Welcome everybody. Don't throw tomatoes at me yet. Save it for to the end. It's a pretty provocative title. Let me state that when I'm using the word Linux in the presentation, I'll mostly talk about the kernel and not about specific distributions, also called as Linux, and very imprecisely. So we have this great Linux kernel, which is not in itself inherently insecure. Lots of security features have been added to the kernel, like ASLR and null pointer dereferencing, protection against null pointer dereferencing. If you don't know what these expressions mean is not a problem. I'll explain them. How many of you have seen András presentation in the other room? Very good. Then I'll explain it. And obviously, there are additional security tools that are not parts of the kernel. These additional tools are Grsecurity and SC Linux. The kernel is not inherently secure because the maintainers of the mainnet kernel is not necessarily the way it should be. For instance, as Linus Torvald said, security people are leeches, showing how in how high esteem he holds security people, and enterprise type functionality is also used on Linux bases, Linux platforms, where turning on security settings may cause applications to not run properly. And obviously, as we know, all business people consider this the first. How many know what chroot is? How many of you know that this is a security tool? So the hacker so there are there are applications that need to be run as root for whatever reason. Another problem is that when an attacker can inject code into our system, then that code will run as root, and in the Unix world, can access anything. One Unix world implementation that looks back on a history of 40 years is chroot, which is obviously which narrows down the accessible file system area, so a program does not see out of a library through the VHF system. The goal of this was to make development easier, because this provides a virtualized environment. Well, it's not virtually virtualized, but the scripts will consider it as virtualized. This Wikipedia quote says that chroot is not necessarily enough to contain a process with root privileges. Escaping from chroot, there are many techniques to escape from a chroot jail. There are extremely simple ways to break out of chroot jail. We have chroot with our application running in it. The attacker takes control. He sees that it's a chroot, then he creates a subdirectory. Why shouldn't he be able to? Roots into it. The pointer pointing to the current working directory will point outwards, out of the chroot. But if we chroot into an internal library, but the current working directory pointer still points outside, and we start stepping always to the parent directory, we will be able to get out of the chroot jail. Because since this is so by design, the only patch I have ever heard solving this issue there's only one such tool. Another, we could also limit a attacker. For instance, limiting mknode. Mknode can be used to create a raw disk device, and then doing this, you can, for instance, create a raw disk device pointing to the primary disk, and you can read or write it from that point onwards. Or you can also directly read or write kernel memory, and you can also use ptrace to connect to a process living outside the jail, and you can make that process do anything you want. The most important thing is that almost all jailbreaking requires root privileges. So protection against it is the following. You should not have root within chroot. This is what Anna Cox said. The problem is that one of the targets of chroot is to run an application that requires root privileges. But we have a beautiful tool called Grsecurity that restricts double chrooting, disabling you to chroot within chroot. It's totally unclear why this has been implemented at all earlier on. It does not allow mknode, no ptrace outside chroot, etc. So this immediately closes all currently known methods, closes out currently known methods for exiting chroot. Grsecurity's chroot hardening measures can be read about at this link. Chroot itself is not a security tool, as Alan Cox notes. On the other hand, the problem is that it is still being used as such. For instance, in the case of MySQL, Apache, FTP daemons have a description about how to chroot it. You have then to copy everything into the chroot because you will never be able to get out of it again. But the system manager will force you to believe that the system is secure while it is not. The next thing that you can use to protect against buffer overflow attacks is rxsplit. It tries to correct the issue of the Norman architecture. The problem being that there is no distinction between data and code. We had an article about this, about how you can use Stack Overflow to take control of badly written native applications. Memory pages should either be runnable or writable, but never both of these at the same time. Implementing this means some overhead, and has, for this reason, not really been implemented widely. The NX bit allows you to mark pages that should not be run. Linux supports the NX bit since 2004, so certain areas to which this segregates actually NX bit segregates areas of memory for use by other storage or process instructions. The goal is to make the system more secure, or to run Java, Wine, or some other applications that does want exactly this, write a memory area and then run it. The problem with NX-bit is that it's not a panacea. the return to libc attack is widespreadly used against it. Love Wikipedia because it sums up the gist of something in a few, one or two sentences. So what this does is, in a traditional buffer overflow, we override the stack with a lot of data, then override the pointer pointing to the next instruction, which points into the stack, and this immediately executes our code pushed on the stack. If the NX bit is set to the memory pages that contain the stack, the NX bit will eliminate this attack, but libc contains functions that are called by the native programmer from the outside, and these are identified as native. So if you select a libc that you know must be there and the parameters are already on the stack, then all you need to do is jump control to that point, and control will be passed to an area that will be inherently identified as runnable or executable. This protection can be enhanced with stack smashing protection that makes sure that the stack cannot be damaged, and it stops program execution before anyone could be able to overwrite the stack. ASLR, according to Wikipedia, is a computer science security technology which involves randomly arranging the positions of key data areas like heap and stack, which would make return to libc impossible because libraries are located dynamically, so the only static thing is the code present in the program itself. In Linux, there is support for this since 2005, but the problem is that its entropy is a lot less than it should be, so it's often not really sufficient. But PAX, the PAX module, supports this functionality since 2001, and they were the first to use ASLR as an expression. And there's also an exec shield patch which is more enterprise-like, which also makes some randomization. But before all of these, it was easy to write exploits to programs and data loaded to the same spaces. The entropy is very small, very little. It's 8 to 13 bits, which we're talking about 256 possibilities, which a current CPU, can crunch in no time. Fork maintains randomization. We are beginning to slip over into mathematics, skip into how to find the segment we want to jump into. We can also create NOP slides. NOP is hex 90 on an x86 architecture, and the CPU will just continue through it to the next instruction. So if we create a long area consisting of purely NOPs, so wherever program control is pushed, or wherever the program control jumps within this area, it will find a NOP and then continue. That's called a slide. And the second method is heap spraying. We put a lot of shellcode into the heaps, and even if randomization is good enough, we might manage to jump to some part of the shellcode. In the beginning, I said that we randomized heap and stack. I omitted libraries because it's not trivial which libraries to randomize when. Microsoft also was very careful about randomization because it may cause compatibility problems. As in the case of Linux gate.so, which was a shared object file, it used to have a static address, despite the fact that all other structures of the program were randomized. And from this point onwards, if there was some usable instruction in the Linux gate.so and there were a good many. For instance, a jump instruction that jumps to the stack. From that point on, if the attacker could inject data on the stack, data that is runnable, but doesn't know where it is, he just jumps to the Linuxgate SO's such instruction, this jump instruction, and Linuxgate SO is told where the stack is, totally annihilating any beneficial effects of total randomization. Linux kernel also has had or used to have something about null pointer dereferencing. OWASP gave me the best definition, which you may know if you're programming in C or Pascal. One of the first things when you are taught how to handle pointers is to not read uninitialized pointers. However, many pointers are initialized to 0 because otherwise some leftover may be there. And this null means that the pointer does not point to anywhere. Algor's designer said that he thinks his life's biggest mistake was to implement null pointers in Algol. CWE writes that in very rare circumstances and environments, code execution is possible. The problem is that these very rare circumstances occurred around the Linux kernel because the kernel uses common memory area with the process actually being run, although the process cannot reach that data because it will be a bit expensive to remap kernel memory areas for each context switch. But page 0 can be addressed by the application, and you can map this area into the address space. And Linux kernel uses function pointers. Any OO programmer will tell you that you can pass a parameter that has a method. Well, Linux has not been written in object-oriented language, so a lot of things have been implemented with function pointers. So if the attacker maps a pointer to a runnable code into this area and then makes the kernel run this because the programmer has not checked whether the pointer was a null pointer, then interesting things may result. In reaction to this, Linux 2623 had a fix called mmap min add, which can also be changed during runtime. There's one problem, that there is a workaround for it. Tavis or Mandy found a nasty bug that affects all Linux kernels, which allowed people on any Linux system to get root privileges. PAX, which is packed with Grsecurity, protects against attack like this with kernel exec on x86 architectures. But on a plain vanilla Linux loved by most people, do not protect with the earlier workaround. Tavis or Mandy found a nice bug in August 2009 that affects all Linux kernels, a lot of them, and is exploitable using null pointer dereferencing. I think this was one of the reasons Linus Torvalds got a brownie. This issue was resolved in kernel 2632. The option allows us to specify the minimal address that can be mapped with the nmap function, and if it is set to any to any value other than null will protect already against null-pointer dereferencing. The question is how many distributions have not implemented this feature. This is a settable value, so the distribution sets it to what it wants to. And if you do not know that there are such kernel parameters or do not know how insecure some of these can be, you won't bother. Grsecurity that I have mentioned so many times is a patch, a set of patches, kernel patches that makes the kernel more secure. Let's restart. So Grsecurity is a set of patches that would like to achieve, is intended to achieve security, specifically in remote access applications. For instance, on systems that only have an embedded Linux and a touch screen, or in situations where users have shell access, so on systems like this, Grsecurity has a security. So the PAX package is also bundled with it, which marks memory pages, as I mentioned with them, when I talked about the NX bit. It flags data memory non-executable and program memory non-writable, RBAC, chroot, and other tools close doors or vulnerabilities that should not be used by design by any applications. RBAC is role-based access control, which allows you to set these access privileges, which may come in handy in some cases. For instance, Linux being root means a lot of capabilities. RBAC can be used to restrict these capabilities and give some programs only the capabilities they really need to run. And finally, it also solves a lot of problems. This solves a lot of problems, but there is one issue here: the default configuration. JSEC will not necessarily make your system more secure, while at the same time maybe it will cause problems. It has a nice configuration area interface, but it is very hard to configure properly, ending up with a system that is nimble enough but also hardened enough. There are some proprietary applications that are examples of this that make life more difficult, and they are not even secure enough. There are competing technologies, one of them being SE Linux. It is also vulnerable in many cases. Pass Audio, for instance, is a case in point. They wanted to demonstrate zero pointer dereferencing. SUIDPA, this is Suite Pulse Audio. The system could be broken not because they hacked into the kernel, but a kernel bug also allowed them to run Pulse Audio, which will then be run as root every time because Suite is set on it, plus the kernel bug caused the system to be broken into. Page 0 was allowed for some programs, and Passadio was one of them. And so, despite the fact that SE-Linux was installed, it could still be owned because pass audio was allowed, page 0, pointing to page 0. Another technology is OpenVZ. Some call it virtualization. I'm not sure whether this is correct, but who am I to discuss, to say it is not? How many of you know OpenVZ? Well, a few know about it. In OpenVZ, virtualization runs on a shared kernel. We have a kernel. We put a lot of users on it, and all of them can feel like they had a separate computer of their own, despite running the fact that he's running on a shared kernel with other users. This does not protect against kernel bugs, because if there are bugs in the kernel, then all of the systems become insecure. So a para-virtualization would be a lot more sensible. Well, that's what I wanted to tell you. Thank you for your attention.